For the next session, for the next technical session, I invite Dr. Neeraj Sharma, Senior Principal Scientist at DRDO DGRE and project leader of Anshakan project, where DRDO is establishing a unique calibration facility for snow avalanche and Himalayan extreme weather conditioning monitoring equipment to be established in Manali. Sir, I invite you as a chairperson of the session. I invite Dr. Saud Ahmed, Senior Principal Scientist and Subdivision Head at Electrical Metrology, LFHF Current Voltage Metrology, Division CSIR NPL. Sir, I invite you as co-chairperson of this session. I request you both to please start the session.
Good afternoon, everybody. I hope I'm chairing a session which is not that boring after the lunchtime in which you had good lunch, all of you. I thank CSIR, NPL, and especially my dear friend, Dr. Sanjay Yadavji, for giving me this opportunity to chair this session. In this session, we'll be having a total of 5 talks. And to start with, I'll invite Mr. Vinod Singh Thakur, who is a research scholar at IIT Indore, for his talk.
Is this audible? Okay. Good afternoon, everyone. I'm Vinod Singh Thakur from IIT Indore. I'm going to present my work at the 11th International Conference on the Advance in Metrology Admit 2022 on the topic of the transfer learning based approach for the health monitoring of the endodontic file using time frequency transformations. And this work obviously I've done under the supervision of Professor Kanka sir and Professor Parikar. And in this study, here we are using the endodontics file, basically what is endodontics file, because there are novel things in that conference we are performing here. So starting from the introduction, what is endodontics file? Endodontics file is a surgical instrument. You can see in that images, surgical instrument which are used by the dental practitioners and the dentistry as well. So you can see this instrument is made up of the NITI also called the nitinol and the shape memorial, which are more flexible than traditional stainless steel. And this was study we are in that endodontic file system where we are using in this work we are using the weapon bolt file and the two shape file. And the both endodontics instruments as well file is the working and operating in the following parameter at the speed of 300 rpm and torque the 5 million centimeter. And the same for the two shape file, it is working. It is operating the 250 to 400 rpm at the torque of 5 to Newton centimeter. And these are the basic introduction of the endodontics file. Moving to the why I'm using this endodontics file and the root canal treatment. So basically, initially I will introduce what is root canal. It is a cleaning and shaping of the endodontic root canal root canalling during the biomechanical preparation. Here we can see that there are three basic steps for the preparation of the biomechanical during the RCT. You can see that the first step, the axis opening. In that axis opening, here we give the initial disk to the air rotor handpiece, which are rotating around 1 to 1.25 x rpm, because it is because for the access opening, when the enamel is the hardest part of the hardest bone of the body, so it's required the very high impact initial disc to require the access opening through the air rotor. Another one is the cleaning and shaping. So cleaning and shaping I've done with the help of the root canal. This is the main process here I'm using for our works. and another one is observation. Because this is an in vitro study, that's why I'm not using the third step. These are the random particles. So because of the constraints in our study, so I'm using only two steps: access opening and the cleaning and shipping. So why I'm doing this study in our work? So because at the present time, real-time monitoring of the mechanical system in vitro study operation had been not much focused upon it, and a few of the literature deal with the force and vibration analysis in the self-consisting file in the simulated root canal and the endodontic file in the with the help of the endotronics block. And to make the analysis more realistic, the real extracted tooth will be employed. It can lead to the better results as what observed by the researcher till date. So here, the initially before performing the study, here I make the systematic review for the AI and ML in endodontics related area. So where is the initially see the initial previous work till that till that area they are cover the researcher till now the determining the working length and the local apical foramens and the retreatment predictions and the prediction of the periapical pathologies and detection and the diagnosis of the vertical root fracture and the assessment of the root morphology. You can see the in all the work, what the work they are doing in AI and ML, they are related. All these work are related to the either they work with the diagnosis of the root fractures or the periapical pathology. Nobody have discussed about the what is the application in the AI and ML application in the endodontics. So here I got the motivation for our work. So in our study, what we are using here. Initially, during the RCT is a root canal treatment. Simultaneously, I have acquired the signal so through the time accelerometer, and thereafter we have done the time. We have did the time domain analysis, and further, we have used the continuous Fourier transform to time frequency domain analysis, and we obtain the images as a scaleogram. This scaleogram I used the VGG 16. This is the 16-layer pattern convolution model. We are using it in that here. So here is the here is the few layers. Which one is the convolutions layer, fully connected layer, and the pooling layer as well as the software execution function. They predict and we give the output of that our study and works. So these are in the previous batch, I have shown you the workflow charts. So how it work in our study, how it's work. So initially when we are performing the RCT, so you can see the images how it look like during the performing the activity. Then after we acquire the signal, so you can see the time frequency domain image like signal, the vibration signals, and thereafter Thereafter, I've done the here I use the CWT technique. So I obtain the scaleogram. This scaleogram we use it for the VGG 16 pre-trained transfer learning model. So and then thereafter I predicted these are I'm prediction for these are the method we are using for the prediction and classification of our work. So how initially for the biomechanical preparation, how we have prepared our sample. Initially, I have discussed the whole study and the motivation for the study. So how we have prepared the sample and for our work. So initially, I took the human extracted teeth. These are the pre-ethical concerns we are taking for that. So these extracted teeth are very, it means it has some germs and healthy. So you have to clean the human extracted teeth. After cleaning with the help of the hydrogen peroxide, here we have the full setting powder and liquid. So simultaneously molding, simultaneously pouring in the mold. After pouring, after a few minutes, we put on the teeth because we require the holding process because teeth is a very unusual shape because we can't directly put on the workpiece. We have to make a mold as a mounting. So here we use the full mounting process. After that, after some time it will solidify, and after removal of the mold, we got the sample, and this is the final sample. After that, we go for the biomechanical preparation. Initially, I already told in the methodology process, and then here I've done the root canal treatment. So these are the whole process how I have prepare our works. So now the next work, how we require the data during the RCT. So in the next works, you can see, observe, this is our the experimental setup for the RCT. Here we have the endomotor hand piece. You can see the endomotor hand piece coupled with the endodontics file. Here we are using human activity. Besides that, we are adjusting to the sample, mounted sample. We are putting an couple and adjacent to the sample. You can see here. Here we are putting and adjacent to the that mountain sample, we have put the accelerometer and we are holding these this mounting and accelerometer into that voice, and these accelerometer are connected to the DAC system for the accelerometer, and simultaneously recorded the signal, and here is the recording the signals, and go for after that we are going for the post processing works. So after acquiring the signal, we are categorizing the three different. After we are uh, collecting the data for the from the accelerometer, here I categorize and choose for the three different class: healthy, moderate, and faulty signals. Here you can see the time domain of acquisition vibration signal during the RCT. You can see the healthy and moderate and faulty signals. So as compared to the faulty, the healthy signals are the has some smoothness in during the acquisition of the signal. But the 45 has some peaks and valley, because there are maybe the chances of the complexity of the root inside during the RCT. So that's why we are, and maybe the instrument failure from at the 3 mm from the tip of the endodontic instrument. That's why we got the and that peak, so many peaks at the faulty point. And thereafter, after categorizing for the time domain analysis, I go for the time frequency domain analysis, because in this analysis we obtain the scaleogram. So you can, here I also observe for the same three different file: healthy, moderate, and faulty file. You can see in that figure clearly visual the magnitude of the frequency is visually seen in the faulty file as compared to the healthy, moderate, and faulty file. At the same, then after these scaleogram here I have used as a images, as a number of images from the three different categories. And these healthy, moderate, and faulty file I have simply categorized the number of samples we have trained for the pre 1060 layer model. We are VG60 model. So then these scaleogram as an image we have feed to the classification model. So after that, we got the training and validation accuracy for the accuracy and loss curve for the pre-1060 layer model. So here you can see the accuracy of that model, and the red color lines shows the validation accuracy, and the blue color here the training accuracy, and the same for the loss curve. We can see here we observe the minimum loss from the model, and after that both the turning and validation curve from the both accuracy and the loss curve for the 60-year model. So here I conclude my study from that works. So here we have evaluated the proposed approach on the required signal and outcome exhibits the effectiveness of the transfer-based technique for the health monitoring of the endodontic instrument during the RCT. And in order to get the time frequency scaleograms from the RCT signal, the CWT is adopted as the time frequency analysis approach. Moreover, the excellence of accuracy in a study on the classification of the time frequency analysis approach serves as another evidence of the signal performance. And this classification result from the VG16 architecture obtained around 87.33 training accuracy and the 85.66 the testing accuracy. According to the obtained accuracy, the technique can be effective for the health monitoring of the instrument while the biomechanical perfusion of the root canal. So these are these are the this study is sponsored by the SERC. So this is the search extremely funded by the Science and Engineering Research Board, DST India, and I wish to acknowledge for providing the financial support to the project under the core research grant schemes. And Still, this is the this actually this is not the in vivo study. So here is the this work is our in vitro work. So still we have take the ethical approval from the committee. So here this is a study has ethical approval by the institution Indian Institute of Technology Indore and the Institute Human Ethics Committee. And these are my references. Thank you.
Thank you, Mr. Vinod. I think Vinod has given us a good insight into the endodontic files health monitoring study for RCT treatments.
Yes, sir.
I congratulate on you on your work. I think this has much future scope also.
I think.
Any questions from the audience? If there are no questions, I just wanted to ask one query. It is not a question as such. What is the sampling rate of the data acquisition system which you are using with the accelerometer in your experimental setup?
So here we are using 51.2 kilohertz for acquiring the signals.
Okay.
And the 4 for all the acquiring for the vibration signal. Whole street for using.
Thank you, Vinod. If there are no questions from the audience, I'll thank you again. Thank you very much.
Thank you. Thank you so much.
Okay. There is a small amendment. Our first speaker, Mr. Mahesh Patil, who is from Amphenol, Hyderabad, he has joined us online. So probably we'll be going for the first lecture now, which was from 2 o'clock to 2:25. We'll start with the first lecture with Mr. Mahesh Patil.
Hi, good afternoon.
Hello.
Yes, can you hear me, please?
Yeah, Mr. Mahesh, we can hear you. You can start your presentation.
Okay, I just wanted to check if I go to the next slide, is it appearing on the?
Yeah, it's appearing fine.
Okay. Give me a minute. I'll just set this up.
Mr. Mahesh, you have 25 minutes to complete your presentation.
Yes. Okay.
Okay, thank you.
Yes. So so this is Mahesh Patil. I am calling in from Hyderabad. Amphenol Advanced Sensors. So Amphenol is a company which traditionally is connector based and then has grown a lot in the sensors and the IoT space in the last decade. And what we do here at Amphenol Sensors is we have sensors for every application, right from automotive, industrial, pharma, medical devices, and right from traditional temperature, pressure to hazardous gas sensors. That's a short introduction. And what we do at Amphenol is a lot of technology and engineering, and there is less of basic research that we do. But here is my paper, which is more on the application and engineering front, which we have leveraged for measurement applications as a sensor company. Um, just to check, is my screen showing the second slide, the grandfather of IoT, the GPS? Let me. Yeah, it is. Okay. Okay. So here before I get into the details of what we do here, the first slide, this slide talks about the before the Internet of Things. One of the most important contribution was from the GPS as a device. And that is where the getting to the location, getting to the position was one of the first disruptive technology which came in, beyond which we started moving from GPS to the Internet of Things. And then it's a lot of dots to connect. The second, which we think really revolutionized this space, was also the internet. Starting from the Moore's law, which we are seeing in everyday electronics that we do, we are able to do really more on a lesser space, and which actually has translated to a cheaper storage, data storage, and the cloud. So that's something which is a short roadmap from Internet of Masses to mobile internet to the Internet of Things. So that's something which, from people connectivity to device connectivity, is where we are. Now, the next slide, which I'm trying to depict, is while we are doing all this work as a sensors, Internet of Things, measurement, security, integrity of the data, it in as we progressed in time, we really lost track of what came first, what came later. But at the end of the day, it was kind of a loop wherein the Moore's law really was the one of the historical turning points, very disruptive in getting the lot of electronics in a smaller space, at the same time multiplying the processing speed and also the cost. While we did this, we talked a little bit on the internet, and what we see today is the 5G, which is coming in rapidly. All of these things put together really gave us the internet, the data, the processing speed, the concept of the cloud. We are able to really do all of these things, move these things from the premise to data anytime, anywhere. And again, the big data, the amount of crunching that we are able to do with all the data, measured data that we have, and bring a really insightful intelligence to this. So as I said, while we put all these dots together, there is one red flag which we always have to be watchful, is how we really bring in the element of security. And when we are moving from on-premise to cloud, the Internet of Things, is the cyber security. The next slide here talks about all these sensors. Now we as a company itself have many plethora of sensors, from temperature, humidity, moisture, to MEMS-based sensors. And all of these sensors are slowly getting connected as devices. And that is where we are coming to the Internet of Things. So as we see here, the number of sensors as we are adding is we are actually also creating a digital nervous system, including the position, including the time, including the data. And that's where it looks like it's getting complex from a sensor element to the electronics to convert to a meaningful data, and then a lot of data crunching to give it intelligence and anytime, anywhere facility. This slide is talks about our wireless loggers. This is a very good latest application on how we are able to really get into a very small device, which in fact, if you see, it can hold 100K samples in that device, which was a few years back was an impossible, uh, it was just not possible. And we are able to really have even the wireless capability in this small device. It could be 5 centimeter by 1.5 centimeter diameter. That's where the Moore's law, the semiconductors getting very efficient and affordable, have been able, really, we are able to get this thing, which is the data capturing thing, the sensor connectivity. You can see these RTDs connected to the sensors, and the temperature range you can see is right from -85 to +140. All of this data ultimately, wired or wireless, gets into that um, device which you see as a computing device. This device can handle millions of data, store data for a long time, and which can actually give reports, which in the earlier days was not possible. It is able to detail reports to extent that we can keep data for 7 years, which is as per the regulation. A real life example of how the old generation, the right side figure shows the old generation of electronics. Old generation these days, or generation could actually change in 3 years. And the new gen actually shows all of that really converted into software. So which really brings in my real estate requirement, my infinite capability to develop huge processing times at a minimal cost. So this is a real life example on how our products have been really changing using these hardware design capabilities, the semiconductor capabilities, and the processing speeds. The next example which I bring on screen is a really very complicated Internet of Things for measurement of temperature and humidity and pressure in an application which today is become vital, especially in the days of vaccine storing, vaccine transportation, warehouse. And this is what it's a completely wireless technology wherein all those devices are able to really capture data, move it to a central location, and it can be accessed anywhere. So this became very vital. It has really the convergence of all the technologies, what we talked before, has really helped this Internet of Things, all these things connected, which can give accurate temperature up till zero point 0.1 degrees C and in extreme temperatures over a period of time. So this is a real life example of how Internet of Things has helped our measurement capabilities for the medical and the pharma industry. More pictorial image on how the compliance in real time looks like. And this is the earlier figure which I showed is a real life, our own products. And this is in a more application way that we use these products. The pace of change, what we were thinking before, I had given a presentation a few years back on how we are working and where we want to go. And while I was doing this for presenting today, I just realized that we are actually crossed 2020. It was around 2017 that I had put up this slide. And that time it was looking like it's kind of a wish list or it could be a very futuristic thing. But the pace of change has been actually much faster than what we see here. The measurements right across from laboratory, storage, production, warehouse, distribution, right up till the customer. It is imperative for measurements which we do in our pharma industry to be accurate, not drift over position and over time. And that is where we have our wireless connectivity, the internet, and the ability to use our electronics and software to give us the seamless connectivity to data to ensure that from source to destination and over a period of years, we do not drift in terms of the accuracies that we have committed for these applications. These are mission critical applications, and we need to ensure that the temperature in which this material is stored, could be a vaccine or drugs, have to be really in a as per the FDA regulations. So this is one of our technologies where we have harnessed all these capabilities, and now this data can be actually seen on any device. So earlier we had a limitation that the device has to have an LCD or a disk or some kind of a memory device. Now it has gone delinked. You actually don't have to see it on the device. You can see it on your mobile. You can see it on your computer, and it has really moved. The platform has moved from on-premise to anytime, anywhere, but not losing any of the efficiencies, accuracies, and all the regulatory requirements that are required. While we have done all this, now the next thing which is really going to help us and how the engineering is going to be leveraged in terms of the 5G. Now, this hyper connectivity that 5G will offer, one of the benefits that we see on the 5G, which we have already started looking at, is how small devices like sensors can actually use the large bandwidth that is available to transmit data. Till the time of 4G, it was an overkill to use that kind of a bandwidth 4G to have sensor data move across the networks. But 5G will give us that flexibility to have narrow band available for us for the Internet of Things. So that's something which is a convergence or an evolution of whichever way we look at to help the small devices where it is unaffordable to use large bandwidths, but use that 5G, the pipe, to really have narrow bands to transmit or leverage the network for our Internet of Things. So this is an ultra low latency which we envisage, and that's something which is going to leapfrog the mission critical applications and the usage. A little bit of why we think 5G will really work for our kind of applications. First is of course, the very low battery and the ultra low latency. One of the disadvantages so far was if you are moving from my lab to a remote location and I want to access the data, there is always a latency, which I think this 5G will definitely help us overcome that. And all the other parameters right up till edge computing, that is something which are already in applications which are used. But this will be help us to decide which will be on the premise, which will be on the cloud, what part of computation will be done on the cloud, what on my device. And this is something which we see as a big benefit or a disruptive technology for IoT applications. So this is an example of how our data, how our Moore's law, how our software computing is helping us in our everyday measurements in our labs, in our customers' premises. And the kind of data that we can crunch, the kind of data that we can present has helped us, has helped our customer. And while we are able to show a year of data in a screen, so that is something which was not possible earlier. But as we see, all these things have really got us to analyze, to predict, and to also monitor and then do some faster work to get this data for a presentable format. The ability to get this in our device on our palm, well, including the graphics. So this is again a convergence of the bandwidth. We are able to get this data on a mobile platform, and with 5G, this is going to really aid. It could virtually or maybe in practical reality eliminate the requirement of device like a computer or a big tablet at the premise. It could be just on the mobile. These are one example of our calibration softwares and how complicated calibration in the lab can be. This shows this is one of our wireless systems, which includes the router, which actually collects the data from all the loggers and then is able to present. So this is one of the examples on how the system looks like, the software system looks like. So while we do all this, there is a lot of work which goes on the background. You can see the software as a service. The first column which shows the traditional IT on premise. Now, this is something which we have been seeing all the time. It is something which is the present situation largely, but slowly we have moved to a level which is the infrastructure as a service. So here you can see that the applications are run by the company, but the storage, the networking is actually done at the vendor's end. So that's kind of the second. The next step is platform as a service, where we actually are moving all the middleware to the vendor. Yeah, the next is the last where is the software as an application service, wherein we actually don't need any of the hardware that has to be run at the sensors company like ours. All of that, the computing minus the sensors can be on the cloud. So that's kind of the evolution. But the kind of work that we really need to build in. While we see that as a block diagram, while we see that as a roadmap, there is a lot of work that goes behind. And this is um, maybe the few tens of engineers working over the years, working on technology and building a roadmap. So that's kind of the evolution on that happens. And on the background, there is a considerable effort which has to be done between the OEM, which is like a sensors company, and a cloud company like a Google or Azure or Amazon. Now, while we do all this, the fundamentals of data integrity, like our applications have a capability to measure up till 0.1 degrees Celsius or lesser. We provide accuracies up to that level. And while we have a huge amount of data, and with this capability, it has been a trend to really have higher sampling times. It could be, we could be reading at one time 48 channels in 1 second, and all of them have to be literally simultaneous and not one missing sample over, say, 3 days of study. If you miss one sample, you have to do the whole cycle again, which means the line or the pharma company which is using this has to do all over again, which could be $1 million of loss. So here is where the reliability of the system, and also at the same time, most important, the data integrity and what we call ALCOA principle, which is attributable, which is legible, contemporaneous. What we say is all the data that we have measured has to be at the same time, and the other things are original, accurate, and complete. While this looks to be a very simple definition, while we put into engineering application, there is where the accuracy of the electronics, the design of the electronics, the reliability of the electronics. While we do this, the testings that has to be done is months of effort, wherein you have multiple systems tested and has to go through an audit which is based on 21 CFR 11, which is an FDA regulation. And data security, and which is this part, while it was on premise, the engineering of this was much simpler, which actually could mean encryption or an authenticated login and make sure that nobody can tamper the data. But as we are moving to the cloud, the data size increases. There is a complete new subject or a complete new platform which you have to work on this
Mr. Mahesh, can you
cybersecurity
hear
stuff.
me?
Yes, please.
Yeah, Mr. Mahesh, you have to wind up in next 2 minutes.
Yeah, I'm almost there. So, yeah, thank you. So the futuristic thing where we go is, if you see this block diagram, all of these things minus the right side is on the premise. The reference, which is the stable temperature bath, the IRTD, which is my reference temperature measurement, which works at 0.025 degrees, and the sensors. So while I'm working with the sensors or calibrating, the left side has to be on my premise. Whereas when I go to the next slide, it is the way things are moving is I can actually have only the sensors, the reference, and the bath in my premise. All the computation can be done on the cloud. The cyber security, I put the question mark because that's an area where which requires continuous attention. The last slide, while we did all this, the Internet of Things, the cloud, the Moore's law, and the extra and the mission critical application and the engineering that goes behind, one thing which has already is most important and contributing factor is the battery. All of these devices require very high density batteries, which can really be at a very lower cost and do much more cycles. So here is where the contribution of the lithium batteries has come in for all the Internet of Things that we see today. So that's more that's on the presentation, and thank you.
Thank you, Mr. Patil, for a nice presentation in which you have covered IoT along with the connected sensors, the networking, coming to the Moore's law, and finally with the battery life. Thank you very much for your informative presentation. Now, for the next presentation, I would invite Mr. Ankit Kumar from NIT Delhi.
Yes, this one. Yes, sir. Good afternoon to everyone. Today I am here to present my work on the 11th International Conference organized by CSIR. My topic is the role of slow MSD waves in hitting the solar coronal lobes using cylindrical model. So this is our outline slide in which we start with the introduction. After that, the motivational observational findings and motivation behind our work. After that, on the basis of these observational findings and motivation, what are the research gaps that we have found, and on the basis of these research gaps, we are proposed some work, and after that, we will explain our work that we have done. And so we will start with the magnetohydrodynamics oscillation. Oscillation is basically when we are perturbed the set of equations. These equations and the waves are going to oscillate, and these waves are MSD oscillations. And these MSD oscillations are basically characterized in two parts. First one is transverse oscillation, and the second one is longitudinal oscillation. So transverse oscillation is basically the type of oscillation in which the wave is propagating in the transverse direction, and there is no compressibility in these waves. We have seen it from there. These are the waves that are not compressible, and the longitudinal wave that we have seen in the below of this slide, these are they showing the compressible and reflection pattern. So these transverse oscillations are are again characterized in two parts, and for structured atmosphere and for unstructured atmosphere. For unstructured atmosphere, that means the part that we have covered in our observational findings are unstructured and non-uniform. And for structured, the part that we have used that is structured, we have structurized this atmosphere based on the density stratification. So these two unstructured and structured atmosphere are their different meaning, and on the basis of these two, they are classified into Alvinic type and Landau type. Basically, for unstructured atmosphere, and for structured, these are going towards the longitudinal oscillation. And these are of two types: fast wave, fast mode, and slow mode magnetoacoustic wave. So our basic aim is to explain here the slow mode, that Alvinic type, Landau, and fast mode that we have done previously, that we have published already. So these are our observational and findings and motivation. So in the previous, in this slide, we have seen that there are many observations regarding the Alvinic wave detection in solar corona. So this particular paper is represent the observation that is on the solar coronal surface. They have detected the large scale observation with the last 2 decades, and they find that the amplitude that they observed is of very less amplitude, is of 0.3 kilometers per second around, and it has less energy to heat the solar corona. But after that, in the next slide, we have the observation that is in chromospheric region and in the transition region. Transition region is the region that is between corona and chromospheric region. From these two observations, we have seen that the detected alveolic wave have have waves have enough amplitude that is of 20 kilometers per second, and have enough energy that is 10 times from the previous one that we have detected on the solar corona. So these waves have enough energy. And for the slow mode, this is the transition region waves that we have detected. After that, we have seen that the fast mode and slow mode waves, and in these some published paper that is they have signifies that the ununiformity in the pattern they have developed for the thermal misbalance, and using the dissipative terms like viscosity, thermal conductivity, and they are doing it for phase conductivity and calculating the phase mixing pattern. But they are doing it for the slab model. So on the basis of these literature survey, we are define some research gaps that are represented. The formulation and simulation of these above, that is alveolic and Landau type oscillations that are doing for the ideal plasma. There is no one that do it for non-ideal plasma. But any situation that is not ideal, so the situation is always non-ideal, but we consider it ideal for our convenience. And in and the for slow mode oscillations, these are detected for the only slab model, but the group that they have originate on the solar surface that are not cylindrical, that are of that are not rectangular. These are of cylindrical pattern. So they have their usual meaning, and on the basis of that, we have designed our proposed work. We have doing the slow mode and fast mode MHD waves for cylindrical model using dissipative terms like viscosity and magnetic diffusivity, and the transverse oscillation for incompressible, and the linear polarization for MHD wave on the basis of non-ideal plasma. So the above three or four proposed work we have already published. Our focus is on the last that we have seen here, the effect of slow MHD waves to heat the solar corona using dissipative terms. So these are our publications that we have done, and this is the abstract we have started with. And sir, this slide is not shown. So please, this slide is not shown here. Yes. Okay, okay. So in this particular slide, we have shown the four set of equations, like the equation of conservation of mass, equation of conservation of momentum, equation of conservation of magnetic diffusivity and energy. And on the basis of this, after linearize these equations, we get these three equations. And after getting the dispersive characteristics from these equations, we are applying the boundary condition on this, and we get two types of dispersive characteristics. On first with respect to the velocity term, and after another respective to the pressure term, that is also not shown here. I don't know what is the problem in slides. So on the basis of these two dispersive terms, we are showing the sausage and king mode characteristics with the density, temperature, and magnetic field variation. Sausage and king, basically the waves that are represented when sausage is the wave is particular towards the one direction, but in king mode there is coupling that is occur between r and theta components in the cylindrical coordinates. So on the basis of this, we have shown the three variations: density, temperature, and magnetic field variations with the period and damping time versus wave number. So in this slide, we have seen that the period and damping time of all these density variations are going to increase, and shows that and the required time that is far below from these observations. So in the temperature slide, there is same pattern that we have shown. From these two patterns, we have seen that in the slow MST modes, the wave does not enough energy to hit the solar corona. But as we compare it with the slab model, so we have seen that in case of slab model, it is far below than the required energy. But in this case, we are very close to this energy. So basically our conclusion here is that in the case of slab model or in the case of cylindrical model is more beneficial than the slab model. So we are using this model and we predicted these waves. And so, and we have enough energy to heat the solar corona. Fast mode have enough energy to heat the solar corona, but slow mode does not have in case of slab model. But in case of cylindrical model, these wave have some energy to heat this corona using dissipative terms. And we have some references on this after the thing.
Thank you, Mr. Ankit. Any questions from the audience? Okay, if there are no questions, I would finally thank Mr. Ankit for his informative talk and on this slow mode magnetoacoustic waves and his study on this. Thank you, Ankit. Now the next speaker is Dr. Kulkarni from TY Patil University, Pune. He's here. Dr. Vinay Kulkarni. Okay, we'll wait for him. And in the meantime, Mr. Rohit Gupta from IIT Delhi is there.
Hello. Hello. Good afternoon, sir. Am I audible, sir? Am I audible, sir?
Yeah, so we'll start with the next talk by Mr. Rohit Gupta from IIT Delhi.
Very good afternoon to all. Sir, I hope I am audible.
Your audio is not very clear. Can you be a bit louder?
Okay, sir. Is this okay, sir, now?
I think you have to check your mic again.
Okay, 1 minute. Just 1 minute. Sir, is it audible, sir, now?
I think we can start with this now.
Okay, thank you, sir. So let me share the slide first. Okay, sir, I hope the slides are visible now. Okay, so very good afternoon to all, and I am Dr. Rohit Gupta from IIT Delhi. I'm going to present my paper presentation on uncertainty assessment of portable EMG acquisition module for hand. So this work is done by our team, which is mentored by Professor Ravindra Agrawal at Thapar Institute of Engineering Technology, Patiala. The content of my current presentation will be like a brief introduction and how we have designed the EMG acquisition system and the experiment design to assess the uncertainty and its related signal processing time. And we will conclude with the results and some of the conclusions. What is the EMG
Dr.
signal?
Rohit, can you hear me?
Yes, sir. Yes, sir.
Dr. Rohit, your voice is not audible properly. You need to check your mic because from our end, it is fine. We just had one online speaker. The audio was good here.
Um, 1 minute, sir. Let me change the mic, sir. Only 1 minute, sir.
Yeah, I think the earbuds are not
ईयरफोन देना है वाला पता नहीं तो सिस्टम में गड़बड़ हेलो हेलो So now it's audible, sir?
Better than the previous one, not that good. I would request you to start fresh again from the first slide.
Okay. So the content of my presentation will be like I will give the brief introduction of my basic paper, then how I have designed the EMG equation system, then the experiment design to assess the uncertainty in the measurements, its signal processing part,
Dr.
results,
Rohit,
and the conclusions.
Dr. Rohit,
Yes, sir.
we are unable to hear you. You kindly check your mic. I think in the meantime, we'll start with another speaker in case he's available for the time being.
Yes, sir.
Mr. KG Jayesh, is he here?
काम कर रहा है यार वो देना ब्लूटूथ वाला देना उसका ब्लूटूथ डोंगल भी देना जरा नहीं इसमें दो वाला है इसमें दो है क्या
Mr. KG Jayesh from FCRI, is he here? He's not here. I think we'll wait for 5 minutes for Dr. Rohit to set up his mic. Mr. Momin, can you hear us? Mr. Momin?
Yes, thank you, sir. Can you hear me now?
Yeah, I think you are giving the talk in place of Dr. Vinay Kulkarni.
Yes, yes.
Okay.
Uh, shall I wait or to continue now?
No, you can start, Mr. Momin.
Okay, sir. I'm sharing my presentation.
You have a total of 15 minutes. After a
Sure.
period of 10 minutes, I'll give you a reminder and
Yeah.
you have to wind within 15 minutes.
Sure. Good afternoon, everybody. Is the screen clear and my audio is also clear to all of you?
Yeah, everything is clear. You can proceed.
Thank you, sir. First of all, I would like to thank you for this selection and acceptance of the paper. So we, Vinayak Kulkarni, Manit Kumar Dhanujay, A.Y. Momin are hereby presenting a paper on thermal stability for a measuring instrument, 3 coordinate measuring machine. The problem content throughout the mechanical industries for the measurement is the correlation of the measurement, the repeatability, the reproducibility, and the dimension differences between two machine, two environment, two places, or two different materials. So this study explains all the challenges and a outcome as a solution what the real practical in the manufacturing setup we studied. Basically, the issues and challenges are seen in the industries are repeatability on the same machine, reproducibility when the time span is changed for the measurement, then environmental conditions when the measurement is done at in-house or the environment at the different customers place. Challenge is to find the correlation in the measurement, and this is mainly because of the thermal drift of the environmental condition and machine and the part configuration. This paper would give us a valuable output to the industry, not only I would say for Indian industry, but it is across the globe wherever the metrology room equipped with measuring instrument where very high precision measuring instrument and the part tolerances are worked with. So in this paper, the temperature stabilization framework is developed. So how we should really understand the temperature stabilization works in a practical approach. This is confined with the machines as a model, bridge kind of the machines. There are various machines models available. We focused where the bed kinematic linkages like machine bed, the y-axis, the x-axis, and the z-axis. This is a kinematic linkage of 3D machine. Then establishing the standard operating procedure for machine stability, reducing uncertainty of the measurement. Stabilization time in a holistic way in one sentence at the beginning to give a outcome to all our audiences and to the world. Stabilization time required by any of the make machine, at least 4 hours stabilization time is required. When we switch on the air conditioning in the morning, or it is recommended late the metrology room should continue all the time air conditioning on. So here are in very detailed literature view we have shown. Because of the time constraint, it is better to go with the major important model of this paper. We selected three kind of the machines, three models. Two are Indian make Spectra 8106, Spectra 564. Also, the variant is kept on the machine for the probing system is a scanning probe continuously measuring, and another is point to point touch trigger measurement. To define the confidence in the research, we have also included a imported model Italian make of almost equal size as 800 by 600 by 600. It gives us confidence the machine make or the place or the model doesn't make any differences. Actually, what this study is, as the problem statement says, the measurement done at one machine at one place, it differs at different, or on the same machine, repeatability and reproducibility, there is no consistency. So measuring parameters in our cycle time of the measurement is done without any of the part. So basically the original structure, including the material of the machine make, is analyzed. Here what we understood is x coordinate, y coordinate and z coordinate, and only the master what we see on the machine at one corner where the zeroing of the scales exactly opposite diagonal is made. So every time the dimension is measured on this sphere, and because of it is only of 25 to 30 millimeter of the diameter size and of the ceramic, so expansion coefficient of the ceramic for the diameter is very less. On the same time, that probability also we excluded. We only taken the linear measurement than the form and the diameter. An influencing factor like room temperature, granite bed temperature, material temperature. Similarly, in all three axes, X, Y, and Z. So monitoring parameters are there and measuring parameters are X, Y, and Z linear. So here you can see the first day of the experiment. It is for the y-axis, the longest axis on the granite bed. And when we started the measurement in the morning, this particularly cycle is from afternoon. And when it starts, after 2 hours of the time, the stabilization is seen. Starting room temperature was measured 24.6 degree. And when the temperature has got stable, after 2 hours of the time, it is 19.3. The reading difference at stable point from beginning was 6.8 micrometers, and the difference in stable span is 5 micron. Now, the complete day data that shows here reading stabilization time is very less when it is continuously switched on, and for the z-axis where the z-axis is a very small cross section. So for the z-axis data.
Dr. Momin, I'd request you to kindly hurry up. You are left with last 5 minutes.
Okay, thank you. So I quickly go to the summary table over here so that I can conclude and the correct output and the message can be given. So what we did over the 10 days of the time at different dates, not only from 1 month, but over the 2 month, different date, the measurement we have carried out in the same fashion, and measurement is done at X direction, Y direction, and Z direction. So the impression, what it shows, the outcome when the room temperature averagely around 24 to 25 degrees and to get stabilized around 20 degrees. Okay, so it requires comparatively less time than the y-axis. Okay, and the y-axis particularly requires around 4 to 5 hours of the time. Okay, so here the minutes is shown. So room temperature at the starting, room temperature when it is stabilized. And when we started the readings, and at that time, after stabilization, what are the differences? So those are computed in a real kind of the data. And here is the last one page summary I would like to add here. When machine in the morning just switched on and the air conditioning is also switched on, the thermal expansion coefficient of expansion of the granite material is 6.5 micron per degree per meter. And because of that, to get it stabilized, the granite bed, when I said the linkages are there, the Y, the X and Z, all the CMMs in the world, any of the make carries a granite bed. In that granite bed, unless and until it stabilizes, the measurement cannot be started. And when without stabilizing, when we start the measurement, then difference of the reading comes around 15 micron, 12 micron. And after the 4 hours minimum, when it is stabilized, it goes to the reading very well stabilized around 3 micron to 2 micron. So solutions derived for problem statement given of repeatability, reproducibility, and correlation of the measurement in respect to thermal stability of the machine. The discussion around the industries at the various customers and the manufacturers is which machine is the good accuracy, good uncertainty, and the better performance. So this paper suggests that it is not the only machine is having the accuracy variation make to make 1 or 2 micron, but the influencing factor and prominently the factor of the temperature, the thermal stabilization of the material of the machine is very, very important. So this is the one point. And irrespective of the machine make and brand, all granite based bridge type CMMs behaves equally in response to room temperature. Thermal coefficient of expansion with uncertainty known is plus minus 10% is all over the world is the same. So depending upon the machine size, at least we would suggest it should be soaked minimum 4 to 5 hours, or it would be better when all the time air conditioning as worldwide is a standard should be maintained in the measurement, the response for the better results, the environmental condition. Unless and until it is not stabilized, what are the risk factor in the measurement? The risk factor in the measurement per meter, the measurement would be different if not stabilizes, that is 15 micron, and stabilizes then 2 micron. So machine accuracies are 1 to 2 microns, so it get the better results. Whereas these 15 microns is the common things between the discussion among us, the customers to customer, and they don't know where exactly is the challenge. So this is the purpose of this the presentations. Hope it is well informed, and any questions can be addressed, sir. Thank you.
Thank you, Dr. Momin. Any questions from the audience, please?
Any question related to the temperature and measurement? Any questions, not necessarily one machine.
I think, Dr. Momin, your lecture was quite self-explanatory. There's one question.
Thank you. Thank you, sir. Thank you.
Hello.
Yes.
When you calibrate the machine,
Yes.
do you consider laser interferometer also for the guideways accuracy?
Yeah, I will answer. Sir, first of all, I would like to your good name, sir.
Dr. K.P. Chaudhary.
Yes. So your question, I just repeat, you are asking the guideways whether already calibrated with the laser interferometer. Is it? Am I correct?
Yes.
Yes. So what I am talking about here, as it is the condition which is already having a calibrated machine, it is not necessary. It has to be calibrated with laser interferometer. Normally, laser interferometer measurement done is for the compensation one time. And also there are the volumetric error compensations. So any of the machine which is already calibrated with any of the means are accurate make machines, we do not even uh, computer aided accuracies are provided for the smaller machine, because mechanical structure guideways we do lapping, manual lapping for the better accuracy. Mechanical rigidity, mechanical straightnesses are computed less than 1 micron. But when the machine sizes are increased, then and then only it required the laser compensations. And that is the reason the laser interferometer is only for the correction of the inbuilt error of the inherent inaccuracies of the machine, but it doesn't varies with the temperature influences. And we are talking only about the linears, x-axis scale, y-axis scale, and z-axis scale. Hope I could make the answer.
But in relation to this question, there
Okay.
are 21 errors in the machine,
21 errors in the machine. Yes.
right?
Yes.
Roll, pitch, yeah, straightness, squareness, etc.
Yes.
But how we cannot all these errors can be compensated using laser interferometer. There has to be certain artifacts, maybe ball plate, ball bar,
Yes.
or step gauge.
Yes.
So, what's your comment on this?
Yes, sir. So what we are in the discussion with you is the calibration process of the machine. And my paper presentation was a different approach. The behavior of the machine at various temperatures and stabilization of the material. But I can answer your questions. There are, according to the international ISO standard TRAIN 360-2, it is a basically series of the standards, and particularly dash 2 is for bridge type of the machine that are recommended to use any of the artifact: length gauge, step gauge, laser interferometer, or as you are talking about the ball plate, hollow plate, or any other artifacts. Those are for the computation and analysis purpose. But for the calibration, they have laid down in the standard a very simple procedure. Take 5-step gauge, 5 steps. equally distributed to the length of the machine. Put in the x-axis. Take 3 readings on each step. So 5 length and 3 times 5 into 3, 15. So similarly, 7 positions they recommended. And the ball plate and the other instruments, what we are talking about, these artifacts are for the analysis of the data, how the accuracies which are mapped or in which zone, what kind of the errors are the residue. So that is a complete different analysis of the machine for the geometrical errors. And what our presentation says is how the machine thermally elongated or contracted over the time with respect to the temperature. If any of the further questions, you are welcome, sir.
Okay, thank you.
Thank you, sir. Thank you very much. Any of the questions, sir, please.
Any other questions from the audience, please? If there are no questions, I would thank Dr. Momin for his talk.
Thank you, sir. Thank you very
I was
much.
expecting this talk because with us it was Dr. Vinay Kulkarni who was to present this. But anyhow, we are lucky to have you with us. Thank you very much.
Thank you, sir. Thank you, sir.
Now I would invite Dr. Rohit Gupta from IIT Delhi again.
Now shall I close my presentation now?
Yeah, you can close.
Yeah. And I now stopped sharing also. Yeah, over to you now.
Okay, very good afternoon, sir. I hope now I am audible, sir.
Yeah, you are audible now.
Okay, so let me share the slides, sir. So I hope the slides are visible, sir.
Yeah, it's visible and you're audible clearly.
Okay, so very good afternoon to all. I am Dr. Rohit Gupta, going to present my paper presentation on uncertainty assessment of portable EMG acquisition module for hand movement design, hand movements. So this particular research has been done by me and Dr. Indrajit Singh Dhinsa sir, under the supervision of Professor Ravindra Agrawal, Thapar Institute of Engineering Technology, Patiala. So the content of my presentation will be like, I will discuss a little bit about the introductory part of the EMG signal, and then the system, whatever we have designed, then the experiment, what we have designed to assess the uncertainty of the designed EMG acquisition module, its related signal processing part, and obtained results with some conclusion drawn from the experiments. So what is the EMG signal? So the EMG signal are known as the electromyogram signal. So
Dr. Gupta, you have a total of 15 minutes. After
yes,
10
sir.
minutes, I'll give you a reminder.
Sure, sir, sure. Okay, sir. So the term myoelectric is drawn from the electric properties of the human muscles, and it is generated due to the physiological variation in the state of muscle fiber membranes. So for normal muscle, it produces a typical or a regular type of pattern of current, electrical current, that is usually proportional to the level of muscle activity. So to acquire these SCMG signal or the EMG signal, we can use two types of electrodes. One is IEMG, intramuscular type of electrodes, which are also known as the needle electrodes, which are used invasively. A needle type electrode which inserted into the human body through that muscle. And second type of EMG electrodes are the surface electrodes, which are used non-invasively over the we can say the surface of the muscles. So these are the non-invasive type of electrodes. So for our research purpose, we normally use these type of electrode. And also in this particular study, we have used these surface electrodes. So whenever we use surface electrodes, normally the EMG is also referred as the SEMG, that is the surface electromyogram. So the general block diagram to conduct the study or to design a system to acquire the EMG signal is like there will be a external circuit which is consist of the protection circuit and the basic filtering part, which reduce the environmental noise. Then the amplification of the acquired signal will be done, and its conversion into the digital form. So for this particular task, the amplification and the digital conversion part, we have used the ADS1298 IC. Then through a particular protocol, like in this study, we have used the SPI protocol, serial peripheral interface protocol, to interface the ADS IC with the interfacing device, which is the microcontroller. And after that, this red block can be, we can say, modified as per our study. So the signal processing part is modified as per our experiment. And if we want to make some decision depending upon the acquired signal, we go for the machine learning part, which consists of the feature extraction, its filtering, its pre-processing part, and the classification part. So we have modified this generalized block diagram as per our requirement. So the block diagram which we have used here is, we have simply take the SCMG electrodes, that is the surface electrode. We have used the ADS1298 IC to amplify the signal and to convert that analog signal into the digital and transmit it to the microcontroller. And then through the USB, we have stored in the LabVIEW or the MATLAB. So for this particular experiment, we have used the LabVIEW part. In the LabVIEW, we have designed the graphical user interface so that the desired parameters for the experiment can be set. So what is the advantage of using this ADS1298 IC? So the major advantage of using this particular IC is that it is a 8-channel IC which have a preamplifier, that is the programmable gain we can define in this particular IC. It has 24-bit ADC. It has a variable range of sampling rate. It depends upon our study what sampling rate we want to use. So for this particular study, we have used 2048 samples per second. It consumes very less power, that 0.75 milliwatt per channel. So depending upon how many channels we are using, the power consumption will goes down. So it uses the SPI protocol to interface with the microcontroller. So only 4 pins are used to interface this particular IC to the microcontroller. So this is the circuit diagram which we have designed. So here we have a pre-filter circuit which is used to discard the atmosphere environmental noise. And apart from that, these are the connections. This is the port where the microcontroller has been connected. So this is the PCB which we have designed, and this is the assembled PCB, and this is the complete module which we have developed in our lab. So here, this is the microcontroller part. This is the designed PCB, and this is the ADS1298 IC. So to connect the microcontroller to the ADS1298 IC, only 4 connections are required. This is the GUI which we have designed to capture or to acquire or to store the signal into the system. So here we can see these are the global channel registers. There are some registers in the ADS1298 IC whose parameter can be changed or modified as per our requirement. So our design GUI provide the accessibility to those channels where the user can define those parameters. Similarly, there we can set the sampling rate, we can save the location where we want to store the data, and acquire and stop button to start the acquisition and to stop the acquisition. Similarly, to change the each channel configuration, that is how those channel are used, what is the gain for that particular channel, this particular front end provide these facilities also. So these are the test signal, internal test signal to test the IC, whether the IC is or the our interfacing is working correctly or not. So this is the test signal which is generated internally from the IC. And this is the external test signal, a sinusoidal waveform we have given to the input side, and the same we have obtained at the output side. Similarly, this is the test EMG acquisition for a particular activity acquired from one muscle. So what are the major uncertainty parameters which we have to consider while developing any hardware related to the biopotential? So one uncertainty can be due to the power supply end. So in this particular prototype, we have used two voltage regulator stabilizer ICs, which at different stages, one at the ADS 1298 IC stage and one at the microcontroller circuit board. So we have measured the power supply for this particular prototype in our lab. So repeatedly, like 10 to 12 experiments, and we have averaged those values, and we have find it is pretty much very close to the 5 volt, which is required for this prototype. And second is the muscle part or the electrode placement part. So one can select a particular muscle and place the electrode at the same muscle, but because of human error, or we can say because of muscle localization error, there may be certain uncertainty between the previous selected muscle or the current selected muscle. Even the person or the experiment who is conducting the experiment want to select the particular location or particular muscle each and every time, but still there is some uncertainty during the electrode placement. So that is considered in our study by taking the different trials, and for each trial we have placed the electrode again and again individually. And due to the subject variation, so to intervene the uncertainty due to the subject variation, we have conducted the study on 10 subjects. So the the experiment protocol is like this. We have considered 10 subjects who have participated in the study, and for each subject, the SCMG signal has been acquired for 10 different trials. So for each trial, the electrode has been placed on the same muscles individually. So for this experiment, we have considered 4 type of hand motion. Um, so one is hand close, hand open, wrist extension, and wrist flexion. These are the 4 major hand motions which should be mimicked with the prosthetic or the robotic arm. So we have considered these 4 muscles to acquire the EMG signals, and then the subject was instructed to sit and relax until he or she felt comfortable to accumulate with the adapt the lab environment. Then the muscle locations has been localized and prepared the skin for electrode placement. In preparing the skin, we have cleaning the particular location with alcohol and remove the hair if required to remove the interference due to the hair.
Dr.
In each
Rohit,
trial,
we have last
yes, sir.
4 minutes left.
Yes, sir, please. In each trial, the total 10 repetitions of each activities has been performed, and the subjects are free to take a rest in between repetitions if required. And in next trial, which took place after 5 to 6 hours of previous trial, step 4, 1 to 4 has been repeated. So the signal processing part is like this. We have acquired the EMG signal at the sampling rate of 2048 Hertz. Then it is filtered using 4th order Butterworth band pass filter in the frequency range of 10 to 450 Hertz. Then it is full wave rectified, and the envelope of the signal has been detected using the 4th order low pass filter with cutoff frequency of 5 Hertz. For uncertainty analysis, we have estimated 2 parameters. One is time domain parameter, that is root mean square, and the other one is mean frequency, which we have estimated. And for uncertainty analysis for all muscles, activity pairs and parameters, in between trials uncertainty and the in between subject uncertainty has been estimated using these formulas. So the results are like this. For uncertainty for trial variation in mean frequency are found like this, and the uncertainty for trial variation in root mean square, that is the RMS value, the uncertainty is found like this for each activity and muscle pair. So if we come to the conclusion, so in this study, we have designed the multi-channel portable cost-effective EMG acquisition system, and we have also tested its accuracy. So as per the available commercially available those acquisition system, the accuracy or the uncertainty shows by them are 2%, and we have found our performance, that is uncertainty, uh, for our developed system very less with respect to commercially available systems. And the repeatability of the RMS value and the mean frequency within the subject had been found similar, and there is found no significant, statistically significant difference. We have applied one-way ANOVA, and the p-values are found greater than 0.05. And also, the uncertainty shown by the mean frequency is more prominent as compared to the RMS value for each and individual experiments. So these are the conclusions drawn from this study. And one more thing which I want to add, that this particular developed prototype or the model has cost around 6,000 to in between 6,000 to 10,000. However, its competent available in the markets are of cost in lakh, at least in lakhs. So in that particular front, our system performed very well as compared to the commercially available acquisition systems. So finally, I am very thankful to the Professor Ravindra Agarwal, Thapar Institute of Engineering Technology, Patiala, for his consistent supervision, and the organizing committee of ADMET 2022 for giving me the opportunity to present the current research. Thank you.
Any questions from the audience, please? I think if there are no questions from the audience, I would like to know which microcontroller you have been using, Dr. Rohit.
Sir, we have used Atmega microcontroller, which comes in the board form, which is TINSI 3.0.
Thank you very much for your presentation, in which you have described about your experimental setup very clearly and given us a good insight into the EMG system. Thank you once again. Now I'll invite Mr. KG
Thank you,
Jayesh
sir.
from CRI, the next speaker with us.
Yes, sir. Am I audible?
Yeah, Jayesh, you are audible.
I think I can. You can see the PowerPoint.
Mr. Jayesh, you have a total of 15 minutes. After 10 minutes, I'll give you a reminder.
Okay. Okay, sir. Good afternoon to the respected dignitaries on the dais, distinguished delegates, and ladies and gentlemen. So I just here to present a topic on the intercomparison program held between FCRI and CSIR NPL Delhi using a mass spectrometer as an artifact. So I'm Jayesh. I'm working as a research engineer uh, in Fluid Control Research Institute. Yes. Hello. Can you hear me?
Yeah, we can hear you.
Yeah. Yes. Yeah. So this numerical comparison is the evaluation of the calibration results of the same item by two or more laboratories in accordance with the predetermined conditions. So in order to establish a national and international compatibility and uniformity of measurement results considerable efforts are being made so that the measurement made in one location is compatible in other locations of the relevant standards. So these are the form of verification of laboratory activities to determine the technical competence. So the major activities involved are the selection of a suitable artifact which has a least uncertainty for the test and identifying the laboratories where the tests are to be conducted. The second stage was the test at the internal laboratories of FCRI. And the third stage, the flow meter which is used for the transfer standard are transferred to the reference laboratory like CSR and for the ILC program. And the fourth stage was for the publishing the data of the result. So these are organized to check the ability of the laboratories to deliver accurate results to their customers. So nowadays this ILC has emerged with the growing need for the comparable laboratory result as one of the most reliable method for assessing the advocacy and the improving the performance of the laboratory. So this by this ILC gives a transparent demonstration of its laboratory's technical competence as far as an accredited body is concerned, and it assists in making decisions on the laboratory proposed capability for the assessors. And as far as the laboratory is concerned, the activity satisfies that ISO 17025 requirement for monitoring of the quality of the results. And of course, it can highlight in other ways, otherwise undiscovered problems and can be used as a development and the improvement tool. So the participation laboratories were water flow laboratory of FCRI and oil flow laboratory of FCRI and water flow facility of CSIR NPL. All the above laboratories adopt primary gravimetric method system as per ISO 4185. So just a brief synopsis. The CSIR NPL, as we all know, New Delhi played a role as a reference testing laboratory in this ILC program. This lab provides calibration of standards and working devices at highest quality of customers from all over the country and abroad. The lab has capability of delivering a discharge of 650 meter cube per hour in volumetric flow rate up to line size 200 mm. And the uncertainty in the flow rate measurement from minimum to 650 meter cube per hour is 0.03 to 0.05%. And in uncertainty volume, it is claimed as less than plus or minus 0.04%. This lab uses a weighing balance of 6,000 kilogram, 3,000 kilogram, 300 kilogram, as well as 12 kilogram for the small measurement. Or as water flow laboratory, it has a specialized of FCRI. It is a specialized test rig for the precise calibration of flow meters, testing of the valves and other flow products. The whole system is designed to handle a maximum flow rate of 4,500 meter cube per hour through the pipeline of size up to 600 mm. So here as NPL, the diverter method is used for the flow measurement, and you can see the snapshot of the diverter system and is the test lines starting from 6 inch to 24 inch or 600 mm and even expandable to 900 mm. So we are using the gravimetric method system of up to 2,500 meter cube per hour with an uncertainty of 0.1%. And above that, secondary system is used, which has an uncertainty of 0.15%. In case of volume measurement, till to 20 meter cube, the uncertainty is plus or minus 0.05%. So here we use weighing balance as a 300 kilogram, 2000 kilogram and 20,000 kilogram system, and even lesser than 60 kilogram and 2 kilogram system, weighing system. For the oil flow laboratories, this has a capability for calibrating any type of flow meters, but the aim was made to calibration of flow meter used for the total volume measurement. That is like a positive displacement meter, turbine meter, master meter, etc., which are used to determine the total quantity of fluid. So this facility makes use of the static gravimetric method system for the measurement, and calibration is performed by, as you see in the figure, is the standing start and stop method. So this facility again is a maximum line size of 200 mm, maximum flow range of 650 meter cube per hour. And for the uncertainty maximum is 0.1%, and the volume determined in uncertainty is 0.05%. You can see one of the mastometer of line 6 inch is assembled in this in series, is assembled in the test rig, and higher size of around 12 inches, 8 inches assembled in the loop. So this facility used for the standing starting stop method for the total volume flow measurement. And regarding the selection of the artifact, the master meter of 3-inch was selection for this ILC program. So this the basic principle of this meter is precisely measure the mass flow of a fluid by vibrating or driving the fluid conveying tube at resonance frequency. So at the flow, the phase shift between the two tubes occurs, and which is directly proportional to the mass flow. And separately and independently, this meter has again provision to measure the density as well. So with these two parameters, like the mass flow and the density, the volume will be measured. So because of this inherent accuracy, minimal maintenance cost, and absence of moving parts to wear out, this meter are usually used in the wide range of application. And to a valid ILC comparison, it is essential that the artifact does not significantly change its measuring characteristics from time the reference laboratory calibrates to when each participant laboratory undertakes the measurement. So due to its positive characteristics and stability, this was used as an artifact. So regarding the ILC program at NPL, as shown in the figure, the mass flow meter was assembled in the test rig, and this facility uses calibration is performed using the static weighing method as per ISO 4185, the flying start and stop method. So before the starting of the calibration process of the flow labs, the system accuracy was ensured before the calibration. So at this process hold was around 5 months, and at NPL itself we could take around 3 days to complete this process. So before the starting the calibration, the accuracy and validity of all instruments was verified, and to establish the traceability of the system and assign the corresponding measurement uncertainty, the individual uncertainty source were thoroughly evaluated. Means for this measurement, the weighing balance, the timer, the temperature, the density, and the timing error caused to the diverter, which is the main significant component of the uncertainty. Every care, or I can say every effort were made to reduce the diverter timing error to improve the overall accuracy of the measurement at each and every lab. And before this practice, the NPL, they have demonstrated this uncertainty of timing error at least 3 or 4 flow rates, three times for the estimation. So initially water will be filled in the meter, and it will allow to warm up for at least 1 hour or to 1.5 hours. And after that, the downstream of the valve will close and meter will be zeroed for any biasing or not biasing. And the meter will be defined as a pulse factor, or we can say the K factor in pulse per kg. So basically, the meter output for a particular flow rate at a prescribed volume, the pulses will be acquired, and these pulses will be divided by this defined pulse per kg, and to get the meter indication. And actual will be with the gravimetric system or the load cell collection tank. Actual mass will be weighed. So this meter totalized volume will be compared with the actual volume, and the error will be derived. So meantime, the meter will be checked, internal parameters of the meter will be checked with the hard communicator or software interface, so that to ensure that the factors are all within the punched value. So this parameter chosen for the comparison is the error in totalized volume. Then this volume was derived at different flow rates from 50 to 150 meter cube per hour. So the next day again for the reproducibility, checking the reproducibility and repeatability, same experiment was repeated. And to check at lower flow rate also, the measurement was further made at 15 meter cube per hour, 20 meter cube per hour, and the 30 meter cube per hour. So criterion for this ILC test is the EN value, which is used as to assess the measurement equivalence between the reference testing laboratory and the participant laboratories. So EN ratios are calculated using the statistical technique like the difference between the lab result and the assigned value, and divided by the RMS value of the participating uncertainty reported by the participant laboratories and the reference laboratory. And as per the NABL guidelines, EN should be less than or equal to 1, which shows that the results are satisfactory. And if it is greater than 1, then we have to repeat the whole process and go for the root cause analysis. But it should be noted that these IELTS inter-laboratory comparison program are not trying to determine which
Mr. Jayesh, you have last 3 minutes left.
Yeah, close to the reference laboratory. Yeah, the comparison of the result was made at different laboratory FCRI, the different labs, and the two labs, the N value was calculated with one of the reference value, and this is with CSI or NPL, and each and every lab, the N value was calculated for oil flow laboratory, 100 ml laboratory, and 600 ml laboratory. You can see that all the values are less than 1. So the graph is plotted. You can see that the black box is the CSR NPL error curve, and all with line within the plus or minus 0.05%. Is the N value plotted with respect to 3 labs. So only the max value is 1. So we can see that the worst case is less than 0.6. That means it is well within the limit. So going to the conclusion part, this comparison shows the close agreement between the measurement results of NPL and CRI. So this mastometer, the artifact shows remarkable accuracy performance in volume measurement in both water and oil. So the accuracy is the meter dependent normalized score. The max deviation between the reference laboratory and participant was 0.04 percentage. The EN value was substantially less than 1 and well within the actual limit. So this result indicates that the liquid flow facilities of CRI are at par with the CSR like national laboratories and international laboratories. So in future, the same pattern test is planned after return of the artifact from NPL. So a final measurement will be made in water and oil flow facilities of CRI to check the reproducibility and repeatability of the meter as well as the system. Thank you. Thank you for your.
Any questions from the audience? I think if there are no questions from the audience, I would thank Mr. KG Jayesh for his talk on interlaboratory comparisons for flow capabilities in FCRI and NPL. Thank you very much.
Thank you, sir. Thank you, sir.
I think with this 6 talks, we will close this session, and I hope you all would gather the best out of this session, which was a mix of people from academia, industry, and various R&D institutes. And I once again thank the organizing committee of ADMET 2022 for giving me this opportunity to chair this session. Thank you so much.
I thank all the speakers for such knowledgeable and informative talks. Now I request chairperson of the session to felicitate the speakers. I request Dr. Neeraj Sharma to please felicitate Mr. Vinod Singh Thakur. Thank you, sir. Now I request you to please felicitate Mr. Ankit Kumar from NIT Delhi to felicitate with conference memento. Mr. Ankit Kumar. Mr. Ankit Kumar is not present. Now I request Dr. Sanjay Adar sir to please felicitate our chairperson and co-chairperson of the session. Thank you so much, sir. We will start our valedictory session discussion since 4:10 p.m.